Hi, class. In Module 10, we study the relationship between two continuous random variables. Here, in Module 10, Lesson 1, we consider a numerical measure of the linear relationship. The objectives of this lesson are to calculate a linear correlation coefficient, carry out the t-test and permutation test for zero correlation coefficient, and then calculate a bootstrap confidence interval for the linear correlation coefficient. So now let's move into our lecture. We discussed the Pearson's linear correlation coefficient. This is the most commonly used numerical summary for the strength of an association between two random variables. And so we begin here. Consider random variables x and y, where the expected value of x is this mu sub x, expected value of y is this mu sub y. Then the linear correlation coefficient between x and y is here. This linear correlation coefficient is a quotient. We take the covariance of x and y divided by the product of the standard deviations. Here, this covariance, we saw this, I believe, in Module 5. You take the expected value of x minus mu x times y minus mu y. We had a shortcut to calculate this as well. And then this product, just as a remark of the standard deviations, we could also write as a square root of the product of the variances. Moreover, you might recall the variance of x, you could write as the expected value of x minus mu x squared, and similarly for the variance of y. For both these, we had a shortcut if we were calculating by hand, but in any case, this is a recollection of these formulas. Now, suppose we have a random sample of paired observations on the two random samples. So they are paired, x1, y1, x2, y2, all together. Our sample size is n. The sample linear correlation coefficient is defined this way. Sometimes you'll see textbooks call this R, but I'm using this rho hat because it is an estimate of the population linear correlation coefficient. You'll notice that if you unravel what the covariance of x and y and unravel the square root of the product of the variances, it looks very similar to the population linear correlation coefficient rho. Now, given a random sample, this sample correlation coefficient reflects the linear relationship between random variables x and y. Now, I have these three examples in my notes, but let's just run them in R. We will get different numbers than in my notes because we will have different random samples, but I like to see it happening in real time during our video. I have three examples to illustrate in R. Let's look at the first one. What I've done is I take X as a random sample from the normal distribution of size 50, mean 5, standard deviation 2. Then I create this error vector where the errors come from the standard normal distribution. My vector Y, you notice I take 2x plus 3 and then plus this error. Okay, so let's look at a plot here. Visually, I see a linear relationship. Of course, it was created this way. Now, one thing about the correlation coefficient, it's always between -1 and 1. Values close to 1 and close to -1 indicate a strong linear relationship, and values close to 0 would indicate no linear relationship. So I expect the correlation coefficient of this sample to be close to 1. Okay, let's see. We can ask the correlation coefficient of this sample. Oh, I did X with itself. Okay, That was exactly one. Of course, it's the exact same sample, but XA and YA, we get 0.982, very close to 1, as we expected from the picture. Let's do another example. Example B. The x's come from the normal distribution, mean 5, standard deviation 2. Now I kept my same error vector, but I just changed it a little bit. I took the cube of each value, so I get a little bit different error. And then my y, I take minus 4 times x, minus this new error vector. Okay, we can once again visually see a linear relationship. Here, this has a negative slope. So I expect this correlation coefficient for this sample to be close to -1. Let's calculate this. We ask the correlation coefficient between XB and YB. I get minus 0.972. Okay, example number 3. This time, X and Y are independent random samples from really 2 different normal distributions. Well, here's the picture. Now we know from theory, if you have an independent capital X and capital Y, the correlation coefficient is 0. Just looking at this picture of the sample, I don't visually see a linear relationship. I expect this correlation coefficient to be close to 0 based on what I see, also based on how I created vector XC and YC. So if we ask for the correlation coefficient of XC and YC, I get minus 0.1. It's a small correlation coefficient here. Now, this was wonderful. We have numbers, 0.982, minus 0.972, and minus 0.1. But we know in this course, we want a hypothesis test. So let's discuss this now. We want to test the hypotheses that either rho, this is our population correlation coefficient, is 0 versus, at least in the two-sided case, the alternative would be that rho is not equal to 0. And we use this test statistic. Now in practice, we will use R, but I list the test statistic. This rho hat is our sample linear correlation coefficient. Now, under the null hypothesis, with X and Y normally distributed, or asymptotically, so large sample size, this follows a t-distribution with n-2 degrees of freedom. We reject the null hypothesis when the absolute value of the observed statistic is bigger than, here this is the 1 minus alpha over 2 quantile of this t distribution. Okay, this table is from the example that I ran in the notes. We can go back to R and see what our exact p-values are for the ones we just created in the video. Every time you run the code that we did, we get a different random sample. Okay, so let's go back to R. We use this core dot test for this test. We can do X capital A, Y capital A. This was, well, you can see the sample estimate here, which we found earlier. This was for the very first example where we had this strongly correlated positive slope in our picture. You notice this p-value, 2.2 times 10 to the minus 16. This is very small. You also see the t observed, and all of these, because my n is 50, our degrees of freedom will be 48 for all 3 different examples. We also see this 95% confidence interval for the population correlation coefficient. The next example we saw was example B, where we had this negative slope. This was the sample correlation coefficient that we calculated. Once again, we have this very small p-value. So in both cases, example A, example B, we reject the null and we conclude the population correlation coefficient is not 0. We also see this 95% confidence interval for the population correlation coefficient. Okay, last one. This was the one where I took two different random samples, independent random samples from two different normal distributions. You notice this is not a statistically significant test. We would fail to reject the null. We can't say that the population correlation coefficient is non-zero. Moreover, you notice 0 is in this 95% confidence interval. Okay, fantastic. Let's go back to my iPad. The issue is, really, this is an asymptotic test. So the question, do we have some non-parametric alternatives to this test? The answer is yes. We can use a permutation test, testing for this null and alternative hypothesis. We could also create bootstrap confidence intervals for the population correlation coefficient rho. These are two separate things. I have both of these built inside our Canvas course. I want to talk about how these differ. So we've discussed very recently permutation tests. We also discussed bootstrap confidence intervals, and they are different but related. So in the bootstrap method, it's important to understand that you have to resample the pairs together, and with replacement, we are creating these pseudo data sets at the same size. So you could take the whole data set, or you could take, in this case, 50 of the very first observation, but you are resampling the pairs. The resampled data set should have similar dependent structure in order to get bounds on the rho. We're trying to create a confidence interval here. Okay, now it's very different when you're thinking about a permutation test, because in a permutation test, we're not trying to keep the dependent structure. In fact, permutation tests were working under H0, which says there's no linear correlation. The permutation test aims at capturing a null distribution for the statistic to address how extreme is the observed statistic under H0. What that means is in the permutation test, you will permute X or Y separately, and there is no replacement. So this is how the two really differ. Let me just show you this and this in R, so you get an idea on the differences in regards to the resampling. So for the bootstrap method, when I do this cbind function, I am pairing the samples. And then what you notice here is I'm just sampling among the rows with replacement. So let me show you this plot. Here would be one example. Now I'm going to do it multiple times. Here's another. Here's another. Here's another. Here's another. We keep going. And these are our pseudo data sets, which we would do maybe 2,000 times, something like this. But you notice the dependency structure is kept. This would be to get a confidence interval for the rho. Okay, that was enough. For the permutation test, you notice what I'm doing. I'm keeping Y vector the same, and I am permuting vector X. Okay, let's go and look at what happens. You notice here, I did not keep the dependency structure. We would do this maybe 2,000 times, and for each time we would calculate a correlation coefficient and use this to get a null distribution of the statistic. Okay, well, we saw that several times as well. That was a fun illustration of the differences. Now, the final thing I want to mention is take care with your conclusions. Even if X and Y have a statistically significant linear correlation, we cannot conclude one variable causes change in the other. And this is one of my favorite XKCD comics, which is related to this. I used to think correlation implied causation. Then I took a statistics class, and now I don't. This other person says, sounds like it helped. And then the original one says, well, maybe. So I will end with that. Thank you so much, class.